Hello friends, today in this video we are going to discuss about impurity or extrinsic semiconductors, right? Or also you can say like dopant atoms and energy levels. So what is the necessity of adding impurity to a pure or intrinsic semiconductor that we are going to see, right? So let us discuss about intrinsic semiconductors. First, we have already discussed it in some other video. We determine the electron concentration and hole concentration in the conduction band and the valence band respectively. Then also we discussed about intrinsic electron concentration or hole concentration in intrinsic semiconductor considering the Fermi energy level, right? So all these things we have discussed in other videos. You can just refer to that for more understanding. Okay, let us now discuss about intrinsic, and when I will call this intrinsic semiconductor to be to be converted to extrinsic, so that way we can say. So the intrinsic semiconductors are the pure semiconductors. Okay, actually, if you will see the use of these intrinsic semiconductors, they are very limited. Okay, why the use is limited? Because of its fixed conductivity. So at room temperature, if you will see, the conductivity value of a pure semiconductor or intrinsic semiconductor is very small, and has a fixed conductivity. You cannot just change the conductivity of intrinsic semiconductor, right? So if we will add some impurity atoms, okay, using the process named as known as doping. You must be knowing this. Doping is what? Doping is nothing but the introduction of impurity atoms. Okay, so this doping, the process of doping, actually is the most efficient and convenient method, okay, to increase the conductivity of the pure or intrinsic semiconductor, right? So depending on types of doping, like what are you actually doping, what is your dopant atoms, right? So you can increase either the concentration of electrons or concentration of holes in the material. Okay, so if you will increase the concentration of electron or concentration of holes, okay, in the material, then you can increase the definitely the conductivity, right? Because these excess electrons and holes generated in the material, okay, these are relatively free to conduct electricity, and hence your conductivity value can be increased. Okay, so what we need to do is, like we can take like pure silicon or germanium, right? Pure silicon and germanium, these are the semiconducting materials, we know that, silicon and germanium. And then you can add any, like group 3 or group 5 elements to it. We will discuss it about it in detail. Okay, how we will add it. Okay, so anyways, so we can add the group 3 and group 5 elements. Okay, so now these impurity atoms which we are adding, okay, which we are adding in the intrinsic semiconductor or pure semiconductor, okay, we'll actually convert this intrinsic semiconductor material to either N type or P type semiconductors, right? So we are going to see how these inclusion of these impurity atoms, okay, or in the process of doping, when you are adding a group 3 or a group 5 element to silicon or germanium, then how the distribution of these electrons will occur, so that you can name it as, you can call it as extrinsic semiconductor. And then we will see how extrinsic semiconductors are of like two types, N type semiconductor or P type semiconductor. So this is what we are going to discuss, right? Now the dopants, when you are adding these dopants with these impurity atoms, like either a group 3 or group 5 element, when you are adding it, okay, the ratio is the ratio means what? The number of atoms you are adding to the intrinsic atom or intrinsic element that you considered, right? So it is around 1 in 10 to the power 6 to 10 to the power 8 atoms. Okay, so if you are considering like 10 to the power 6 to 10 to the power 8 atoms of intrinsic material, silicon or germanium, then your dopant atom will be 1 in 10 to the power 6 or 10 to the power 8. Suppose you are adding a group 3 atom to this silicon, then one group 3 atom you are adding to what, 10 to the power 6 to 10 to the power 8, okay, atoms, okay. So this is the ratio actually we keep, okay, in the process of doping, okay. So what is the objective here? Objective is to alter or change, okay, the conductivity of the semiconducting material without any structural change of the intrinsic material, okay. So we are not making any structural change of silicon and germanium in the process of doping, right? But by adding these impurity atoms, you can see that the conductivity of these materials can be enhanced, can be increased, okay. So that is overall, like, the objective. So what is the objective? By adding impurity or dopant atoms to the intrinsic material, okay, we can increase the conductivity of the materials at room temperature without affecting its structure, okay. So this is what we said, right? This is the process actually we are going to discuss. So now let us first discuss about the donor or n type semiconductor. What will happen, what is that donor electron, or what do you mean by n type extrinsic semiconductor? Extrinsic semiconductor is simple, we said, when you are adding some impurity atom to the intrinsic semiconductor, we called it as extrinsic semiconductor. Then I told you there are types. So n type. Okay, so what is n type semiconductor? N type semiconductor, and what do you mean by your donor electron? Okay, conductor, or let me just write slash or donor. Okay, what is a donor or donor electron? What do you mean by this? We are going to discuss this. Okay, so now here, what will happen if you will take, like, suppose I will take a silicon, okay, and what is silicon? We know, if you will consider the valence electron in silicon, right? The valence electron, four valence electrons are there in the valence, in the, sorry, the outer orbit, or the um, outer orbit, yeah. So four valence electrons silicon will have. Then suppose you will add a group 5 element to it, okay, a pentavalent impurity. Group 5 means, of course, pentavalent, where you got in the outer orbit you have 5 electrons, right? So what will happen if you will take this, right? So if you will add a group 5 element, such as, group 5 element, we can take, like, phosphorus we have, like antimony we have, arsenic we have, right? So if you will take a group 5 element, okay, and we'll add it to what? To silicon atom. So you will add it to silicon, right? So group 5 element, for example, as I said, you take phosphorus, okay, or you take antimony, or you take arsenic. These are all pentavalent arsenic. Okay, these are called these are pentavalent atoms. So you can see, like, if you'll add this to a silicon, which is having actually 4 electrons at its valence shell, so what will happen, right? So now you see, suppose I'm just showing you the, suppose the outer orbit. So you have electron over here, one electron in the here, one electron, suppose randomly I'm just showing you. Okay, these are the 4 valence electrons that silicon is having. Now suppose I will add phosphorus to it. Okay, phosphorus, we said there are, you know 5 electrons. Okay, 5 electrons. I'm not following any particular pattern, I'm just writing it. This electron, extra electron, you can see this is the 5th electron I just said. Okay, so now when these this phosphorus atom, okay, will be introduced to silicon atom, okay, or we said will be doped into silicon, then what will happen? You will see that these this electron will come, will share the bond, so it will form covalent bond, right? So four of these valence electrons of silicon, you can see, okay, they will be combined with these four, 1 2 3 and 4 electrons of the phosphorus, right? So four of these silicon valence electrons of silicon, okay, will contribute to the covalent bonding, okay, with the silicon atoms, right? Now what happens to this one? This is now is left, right? So this particular electron is very loosely bound to the phosphorus atom over here. The others, what happened, they they form bond, they share the electrons and form covalent bond, right, with the silicon, the valence electrons of the silicon. But this particular electron is now loosely bound, okay, loosely bound to the phosphorus atom, right? Now okay, now what will happen? This particular electron, actually we named this particular electron is the excess electron, okay, which is not actually taking part in any bond, like in covalent bond, right? Okay, so this particular electron we called it as donor, okay, donor electron. This particular electron is known as donor electron. So we got this donor electron here. Okay, so when you are adding pentavalent impurity to silicon or germanium, four valence electrons of silicon, they share four, shared with, or they shared these their electrons with the four other electrons of phosphorus, but there is only one electron left which has not participated in any bonding. So that is loosely bound to phosphorus and we called it donor electron. So why this is known as donor electron? Because at very low temperature, okay, at very low temperature, this donor electron is actually bound to the phosphorus atom, to this particular phosphorus atom. So this electron is bound, right? And the amount of energy that is required, okay, required here to what? To make this electron elevate, or to make this electron free, okay, free from this, this loosely bound force over here, okay, and to make it free to move to the conduction band is considerably less, very less, okay, than that of the electrons those are involved in the covalent bonding. So we said all these, four electrons here, they are all involved in the covalent bonding. So the force actually to require, the energy required to make those electrons free is actually larger, okay, than the force or the energy that is required to make this electron free and make it move to the conduction band. Okay, so relatively this energy required is less. Okay, so what will happen here now? So we can say, like, what is the amount? I mean, if you just make an estimation, like what is this, what is the amount of energy here? Okay, what amount of energy is actually needed to make this electron free? Okay, to make this electron free from phosphorus and to take it to the covalent bond. Here actually the amount of energy is very less here. And if you will see, like, if you will see the energy, actually the energy gap, if I'll show you in terms of like bands. Okay, let me just draw it. For example, this is your conduction band in semiconductor, we know that. So already in one video we have discussed the structure of the band. So conduction band, you have valence band over here. Then you said this is the mid gap, okay, in between, that is also derived in one of the videos, you can see, right? So the amount of, in a semiconductor like silicon and all, it is of the order of 1 electron volt. Okay, this gap is of the order of 1 ev, 1 electron volt, the energy gap between conduction band and valence band. Now if I will do it for like silicon, if I'm adding phosphorus impurity to silicon, then you will see these free electrons, okay, they will be, all these donor electrons will be in terms of energy. If I'll just show you, the bands are actually giving you some energy values here. Valence band gives you particular energy value, conduction band corresponds to a particular energy value. Here if I'll write this is the energy of the donor electrons, okay, donor level, okay, then you will see here this particular gap. Okay, the gap between the conduction band and the donor energy level is very less. And for silicon, actually it gives you what, it gives you a value around, it's approximately 0.03 electron volt. So 0.03 electron volt actually. And for germanium, this value is actually around 0.01 electron volt. So roughly we can say, actually you see This is 1 electron volt of the order of 1 electron volt, and this is of the order of 0.01. So 1 upon 100, 1/100th of this value. So you can imagine this value actually here is very, very less. So the gap here between the conduction band and the donor energy level is very less. So that's why we said loosely bound, very loosely bound actually. So even by little thermal agitation, okay, these donor electrons can actually be elevated to the conduction band. So these donor electrons, these extra electrons, we said we are adding one atom to what, 10 to the power 6 to 10 to the power 8, 10 to the power 8, okay, silicon atom. So one impurity atom for 10 to the power 6 to 10 to the power 8 silicon or germanium atom. So now the number of dopant atoms you added, they will all give you these donor electrons, and these donor electrons will be there in the donor energy level, which is just below, below the conduction band by an amount of 0.01 electron volt, of the order of 0.01 electron volt. So these electrons literally, require very less amount of energy, or you can say a thermal agitation. Okay, a small thermal agitation can actually push these electrons to the conduction band. Okay, so that is what we said, and all these electrons, they are known as the donor electrons, and they correspond to a particular energy level over here, and we said that's the donor energy level. Okay, so that's the donor energy level we said. So so the electron in the conduction band, now you consider, suppose I will consider room temperature, right? So room temperature, or we said around 300 Kelvin, right? So if you will consider 300 Kelvin, the amount of energy that is gained by these donor electrons is enough, so they can easily be elevated to the conduction band. Okay, to the conduction band to conduct electricity, or we said to affect your conductivity of the material, right? So here what we said, we have the conduction band over here, conduction band, then we said the donor energy level is very close to the conduction band. This is what I'm writing as ED, the donor energy level. Okay, let me just use the as usual notations that we are using. So this is your EC, okay. So the energy corresponding to the conduction band, and then your EV, that is the energy corresponding to the valence band, and then this is ED, the donor energy level. So now what will happen? You said you have electrons over here, so you added the dopant atoms, one atom per 10 to the power a 6 to 10 to the power 8 silicon or germanium atom. Now at T is equal to 300 Kelvin or room temperature, what we said, we said these electrons will actually be elevated, right? Will be elevated because thermal agitation is sufficient, because the amount of energy is very less, and we said of the order of 0.01 electron volt, right? So you can see these electrons can easily be elevated. Okay, so can easily be elevated from here. So when these electrons will be elevated and will move to what, and will move to this conduction band, what will happen? These are actually phosphorus related to the phosphorus atom. These are the electrons that we are getting from the phosphorus atom. So here in the energy level, here donor energy level, they will leave what? Immobile positive charge carriers. Immobile positive charge or positive ions, we say. Okay, so remember these are immobile positive charge. Here we will not consider this to be holes, right? They are not free to move. That's why we said immobile. Okay, so now what happened, these electrons in the conduction band, they will they will contribute to the process of conduction. So they will give you like current. Okay, so while these positively charged ions, okay, that we got in the crystal, okay, these are immobile and these are fixed. These are immobile and these are fixed. Okay, so these positive ions over here, ions in the crystal, okay, are fixed and immobile. So this is what you need to remember. Do not ever consider this to be holes. Okay, holes are actually what? The vacated electrons in the valence band, and they are free to move here, and they, they are the charge carriers in the valence band, and they contribute to the process of conduction. But not here. Okay, not here, not the, the ions here in the crystal which you got in the donor energy level. Okay, so these these impurity atoms, actually what they did, impurity atoms that we added, they actually donated these electrons, right, to the conduction band. Okay, that's why we call these atoms as donor impurity atom. So simple, donor impurity atom. So now you can say, or you understood what is donor impurity atom, right? So now the donor impurity atoms, what they did, they added electrons. So what they did, they added more electrons. They added more electrons. So more electrons to the crystal, right? So they added more electrons. Before, you took only intrinsic semiconductor. So intrinsic semiconductor, you have at room temperature only a fixed value. In intrinsic semiconductor, you had only a fixed value of number of electrons in the conduction band, right, at room temperature at 300 Kelvin, for example, we take as the room temperature, right? But when you doped this intrinsic semiconductor with what, using the process of doping and adding dopant atoms to it, right, you got extra electrons, right? So added more electrons to the crystal, you got extra electrons, right? So you got extra electrons, or excess electrons, I would say excess electrons. Okay, without creating any holes. You are not creating any holes, without creating any holes. But what you created, you created these ions. Okay, positive ions were created actually in the donor energy level, because of the thermal agitation, and this value, the energy required to move to the conduction band is very less. So all these electrons require actually very less amount of energy, and they can move to the conduction band easily. So in the process, you actually created what, immobile and fixed ions. Okay, immobile and fixed ions. So without creating holes in the valence band, in the valence band. Okay, so this is what we did. So by adding more donor impurity atom, what you did, you increase the concentration of electron, or number of electrons in the conduction band, without creating holes in the valence band, right? So now if you will see, in an intrinsic semiconductor, what happened in an intrinsic semiconductor here. Okay, you had the same like conduction band, and you have the valence band, right? So at 0, we said valence band is completely filled and conduction band is completely empty at 0 Kelvin, right, at 0 Kelvin. But if we will consider room temperature, suppose 300 Kelvin, and this gap, actually energy gap for silicon, is some around order of 1 electron volt. And if you actually take the room temperature to be 300 Kelvin, few of the electrons will be there already in the conduction band. Okay, conduction band. Here you will get these holes. Here you got these holes, and these holes are actually what, vacated electron, or we said these positive charges. We consider this to be positive charges, and they, here in the valence band, they can move and will contribute to the process of conduction. Same way like the electrons will move here in the conduction band to contribute to the process of conduction, holes will move here in the valence band to contribute to the process of conduction, right? So this is what I had I mean, in intrinsic semiconductor, that's why we said the number of electrons here in the conduction band and the number of holes in the valence band are actually very limited. So the concentration of the charge carriers in the conduction band and valence band are limited, and hence the conductivity is also limited. So we added donor impurity atoms to it, right? So donor impurity atoms, what donor impurity atoms did, actually they gave you some excess electron. Okay, excess electron. So you got some excess electrons in the conduction band, as per the the concentration of what, the impurity atoms, right? But here you got only what, the immobile and fixed, ions over here. Okay, remember, these are not holes, these are immobile fixed ions in the crystal, right? So what we did, we didn't create any holes over here in the valence band in this process of adding, donor impurity atom to the intrinsic semiconductor, whereas we increase the concentration of electrons in the valence band, right? So the net value of the electron concentration, if you'll see, or the net number of electrons that is there after this doping, you can see has increased. Okay, this has increased without creating any holes over here. No holes over here were created in this process. So you can see the concentration of electron, if I will write N, and the concentration of hole, if I will write P, then definitely the concentration of electron here is more than the concentration of hole. So this type of an extrinsic semiconductor, where you added donor impurity atoms or pentavalent impurity atoms, or you said group 5 element to silicon or germanium, then you added more electrons, donor electrons, to the conduction band, and in the process the concentration of electron actually you increased without creating any holes in the valence band. So the concentration of hole in the valence band remains the same, but the concentration of electron in the conduction band has actually increased. Okay, so this is what is the process of doping, and the way you can create actually a n-type semiconductor, which is a type of extrinsic semiconductor. Okay, and we discussed about donor electrons. What do you mean by donor electron or donor impurity atom? Okay, so in the next video we are going to discuss about, the acceptors. Okay, acceptors or the p-type semiconductor, the same way exactly. So if you are adding, a group 3 element to, like boron or then what will happen to the concentration of electrons and holes, that we will discuss in the next video. Thank you for watching. Please subscribe this channel. Thank you.